Hello my dear students. In this video, I am going to explain the last part of compiler design. In the module 3 and 4, we have studied first three phases of the compilers, that is lexical analysis, syntax analysis as well as semantic analysis. So last module, that is last part of compiler design, module 5 covers intermediate code generation, code optimization and code generation. So in this module there are 5 chapters we need to discuss. This covers syntax directory definition, evaluation order for SDD, application of SDD, variants of syntax trees, tree address code, issues in the design of code generation and the target language. Here this is the chapter Syntax Directory Definition, which is helpful to study the implementation details of the compiler. So here in the next chapter, sixth chapter, we are going to study one of the intermediate representation which is called as syntax tree as well as tree address code. And in the last chapter, we are going to study about issues of the code generation. So we are going to discuss in brief itself. Coming to syntax directed definitions, the syntax directed definition is nothing but CFG. You know what is CFG? It is nothing but context free grammar. And a CFG together with attributes and rules is called as syntax directed definition. So now let us study what are attributes and what are rules. Attributes are associated with grammar symbols, and grammar symbols, please remember, grammar symbols may include terminal or non-terminal like a capital letter E or small letter ID, like that. And rules are associated with the productions. Suppose I have the production E gives E plus T, then E plus T is a production. So in the syntax directory definition, rules are associated with the production, whereas attributes are associated with the grammar symbols. So in my example, E gives E plus T, E, then plus T, etc. are the grammar symbols. Now an attribute has a name and an associated value. Whenever we say syntax directory definition, in short I will call it as SDD. SDD. It contains attributes, right? So that attribute has a name and value. So value of an attribute may be a string or a number or a type like data type or a memory location or assigned registers like R0, R1, R2, etc. So attribute has a name as well as value. Now for example, if X is a symbol, grammar symbol, and A is one of its attributes, means values, then we write X dot A to denote the value of A at a particular parse tree node labeled X. Okay, X is a grammar symbol and A is the attribute, then we will write X dot A. For example, our let us consider the grammar, arithmetic evaluation grammar, E gives E plus T. So if suppose it is arithmetic expression grammar, then E may hold a value. So I can write E dot value. So dot val or dot value is nothing but attribute. That means grammar symbol E may hold a value. I think you understood. Okay. So X is a grammar symbol. I will consider E. So E dot, then attribute value is val I will consider. So these are the points about SDD. They are highly readable, understandable and give high level specification for translations. But there is small disadvantage of SDD. They will hide many implementation details. Difficult to implement if we have only SDD. We require some other part to implement this phase of the compiler design. For example, they do not specify order of evaluation of semantic actions. For example, in the arithmetic expression grammar, we know some rules, right? Multiplication, division should take place plus after, then addition and subtraction, like that. But this SDD will not say about evaluation order. So what to do? We have another level called as SDT, syntax directed translation schemes. So what is SDT? SDT, it is a program fragment called as semantic actions within the production bodies. Suppose we have E gives E plus T. E plus T is the production body, right? Production body is E plus T. It can be followed by some semantic actions. What to do? Actually, it is the evaluation E plus T. E plus T must be evaluated. If you want to print the result, then you can write print result. Okay, that print result is nothing but semantic action. Now the position where we have to place the semantic action, it determines the order in which the action is executed. If you want to print E and T in the beginning, you can include the action in the beginning. If you want to print the result at the end, after writing the body of the production, you can print. Consider this example. Rule E gives E1 plus T or E plus T. After this rule, I want to print plus because just to indicate that it is an addition operation. So, this production rule is followed by semantic action print plus. Semantic action is always written with the help of flower brackets. If you want to have this action in the beginning, you can write over here print plus then followed by E1 plus T. Okay, in the middle also if you want to write, then write E1 plus T, or for this one you can't write this action in the middle. So for some other productions if you take, then you can write the action in the beginning also. SDTs are more efficient. Some important point related to SDT compared to SDD. They are more efficient than SDD as they indicate the order of evaluation. So this in this particular example, printing will be taken place after evaluation, like that. So they will indicate the order of evaluation and associated with the production role. And one more point, this also gives some important information about implementation details. If we have SDT with us, that means semantic actions with us, then programmers can implement the particular task easily. So this is about SDD and SDT. SDD is syntax directed definition, whereas SDT is syntax directed translation. Now, what are the types of attributes? We have already studied that an SDD may contain attribute. What are the different types of attributes? Students, please consider this as very important topic. That is, explain different types of attributes with the example. Now, what are the two types? One is synthesized attribute, another one is inherited attribute. What is synthesized attribute? Synthesized attribute for a non-terminal A at any node n is defined by a rule associated with the production at n. That means if we have a production E gives C plus T, then how will you write the parse tree? Parse tree can be written as E, then E gives E plus T. So here synthesize attribute means E plus T will be evaluated first and its value is stored in E. That is, we are passing the value from bottom to top. So synthesize attribute is always helpful for finding the value using bottom up parsing, finding the value of a non-terminal using bottom up parsing. See, one more important point here, a synthesized attribute at node n is defined only in terms of attribute values at the children of n and n itself. In our example, E plus T are children of E. So children nodes are evaluated and value will be stored in E. Okay, I think you understood. Let us see the example in the next slide. So this is about synthesize. So please remember some points regarding synthesize attribute. Synthesize attribute is helpful for bottom-up parsing. Children node value is evaluated first and it is stored in the parent value. That's why the definition. It is defined only in terms of attribute values at the children of n and n itself. Now coming to inherited attribute. What is inherited attribute? For a non-terminal B, at a parse tree node n is defined by a role associated with the production at the parent of n. So here production must have B as a symbol in its body. Here A is present as LHS. A as its head means LHS. We are defining synthesize attribute for LHS non-terminal, and in a different way inherited attribute is always defined for a non-terminal which is on RHS. And one more important thing, it is defined only in terms of attribute values at n's parent, n itself and n's siblings. So here using inherited attribute we can pass value from top to bottom, that is parent to children nodes, or siblings, n's siblings, that is left to right. If we have 3 children nodes like this, then we can pass a value from this node to this node, or we can pass a value from this node to this node, and according to this n's parent and n itself we can pass a value from root node to its children node, whereas this is not possible in case of synthesize attribute. In synthesize attribute, how it happens? Synthesize attribute, if we have children node like this is the root node, these 3 nodes are evaluated and its value will be passed from children node to parent node. So this is the difference between synthesized attribute and inherited attribute. In the next slide, let us see the difference between these two types of attributes with the help of columns. First two points, these 2 points are related to the definition as I discussed with you earlier. Now consider the example. E gives E plus T or T. If this is the production, then synthesize attribute how to write E dot val, and please students please note down this val can be written as syn. Syn also means it is a synthesized attribute. Let it be, it is val means the value will be stored in node E. It is given as E dot val plus T dot val. Then according to this E gives T, one more production is there, no? It is written as E dot val is equal to T dot val. T value is assigned to E value. Then see one more thing you can observe here. In synthesized attribute, we can have an operator plus in between two operands. Okay, bottom up parsing we can have left recursion, left factoring and all, no problem. So conditions will apply for only top down parsing. So since synthesize attribute can be used for passing value from bottom to top, we can have the productions like this, having left recursion or left factoring. So that is one important point you can note down here. Operator can be present in between operands. Consider inherited attributes where we have to use inherited attributes. So T gives ft dash. So actually this is written by removing left recursion. For example, consider T gives T star f or f, then f gives id. If you have production like this, then how will you remove this left recursion? T gives ft dash, T dash gives star ft dash or epsilon, right? So since inherited attribute are helpful for bottom up top down parsing, we have to remove left recursion like this. So we got this production t gives ft dash. So just that part I am going to use here, ft dash. You can observe here there is no multiplication symbol in between f and t dash. So how exactly the multiplication takes place? It takes place in the next step. Observe this grammar. Multiplication will take place in the next step. So we have to pass value from one step to another step. Means one node of the parse tree to the children node. So t dash, and one more point according to this definition. Observe that second difference carefully. Sorry. Okay, here we are. Second difference is that it is defined only in terms of attribute values at n's parent, n itself, and n's siblings, right? And b as a symbol in its body. Now we are going to write inherited attribute for t dash. T dash dot inh. So dot inh means it is inherited value, inherited attribute. To represent inherited attribute, we will use inh. What is t dash dot inh? It is nothing but f dot val. Means the value which is present in f is copied to t dash dot inh. Then this t dot val, how to represent this t dot val? It is nothing but t dash dot syn. Why it is made as synthesized value? Because multiplication takes place in the next step, children level. From children level we have to pass the value to the top level. That's why we require synthesized attribute also. And just usage of only inherited attribute is not possible. If we are going to use inherited attribute, sometimes we may require synthesized also. But just by making use of only synthesized attribute is always possible. So another difference, used to pass a value from bottom of the parse tree to the top of the parse tree with synthesized, and with the inherited either top to bottom or left to right. And it is suitable for bottom up parsing and it is suitable for top down parsing. These are the differences between synthesized and inherited attribute. Now we'll see example for synthesized and inherited attribute. This is example for synthesized attribute. This is an SDD which involves only synthesized attribute is called as S attributed. Okay, now consider our grammar, well popular grammar, arithmetic expression grammar. E gives E plus T, E gives or T gives T star F for F gives parenthesis E or digit or ID, okay, whatever may be. This is our arithmetic expression grammar. How to write semantic rules for this grammar? Now, since the grammar is suitable for bottom-up parsing, which contains left recursion and all, we need only synthesize attribute. So L gives E. See, remember this one more thing. This N is there, no, just to indicate end of the string. Okay, nothing else, end of the string. So L gives E means final value which is present in this node E is copied to L. Okay, start symbol is L. If we use start symbol E, then we have two production E1 plus T as well as E1 plus T as well as T. So to avoid confusion, we are making use of one more start symbol L. Okay, like our LR parsing augmented grammar. Okay, it's fine. Here, what is this E dot val? It has to be copied to L dot val at the end. Okay, so L dot val is equal to E dot val. First rule. Second rule, how to write the second semantic rule? E gives E1 plus T. So, E1 and T will be evaluated and it is stored in E. So, E dot val is given by E1 dot val plus T dot val. You can write just E also, just to differentiate between this E and this E, we will make use of E1. Similarly, E gives T rule. E dot val is equal to T dot val, just an assignment. Okay, then T gives T1 star F. So T dot val is equal to T1 dot val into F dot val. T gives F, just assignment. here also f gives e, parenthesized e. We are not going to make any operation over here, just an assignment. So whatever value is present in this e will be copied to f. Then the last one, f gives digit. Note down here, f, what is f dot val? It is nothing but digit dot lex val. Why we are writing like this lex val? Because this is the value which is obtained from the lexical analysis. Just to identify that it is the value obtained from the lexical analysis, we are writing digit dot lex val. So this is the SDD for desktop calculator or simple desk calculator. And you can observe one more thing here. Here no multiplication or subtraction operation have been used. You can make use of minus and star to complete desk calculator. Okay, understood, right? Only plus and star they have used. You can include minus and star. How will you make use? Even plus t or even minus t you can add. So for even minus t, you write the rule e dot val is equal to even dot val minus t dot val. Here t star f, one more rule, t1 divided by f. So here add one more rule, t dot val is equal to t1 dot val divided by f dot val. So this is an example for synthesized attribute. Now somewhat complicated one, inherited attribute. So as I told you, inherited attribute is applicable for top-down parsing. Okay, consider this grammar. T gives T star F for F, F gives digit. This is not suitable for top-down. Why? It contains left recursion. So remove the left recursion. After removing the left recursion, we have the grammar, this one. T gives ft dash, T dash gives star ft dash, T dash gives epsilon, and F gives digit. Okay, this is the grammar which is not suitable for top-down parsing. So we have removed left recursion. So this is our resultant grammar. Okay, how to write the rules now? Now consider this example 3 into 5. I want to find out the value of 3 into 5 multiplication. So how can I use this grammar to find out 3 into 5? I can easily write a parse tree. T gives ft dash, right? T gives ft dash. There is no other option, only one option I have. Then I have to use for this f digit dot lex, f gives digit. This production I need to use. So digit dot lex val. For t dash I have to use this production. So star ft dash, this t dash will be epsilon and this f is 5. So one operand I have here and another operand is here. Multiplication take place in this step. Okay, observe clearly, one operand is here, another operand is here. Okay, if I divide this tree into two parts like this one I will call as LHS, this is RHS. Okay, left hand side and right hand side, I'll rub once. One minute. Okay, in between I will put a line over here like this. Okay, one operand is here, another operand is here. So multiplication takes place here. We need to pass a value from left hand side to right hand side as well as bottom to top. Right? Multiplication takes place here and then finally we need to store the value here. T dot val is equal to 15. So to make use of all those things, compute the values like this, we need inherited attributes. See here, digit dot lexval is equal to 3. This 3 has to be copied to f dot val. By using this rule, we can get f dot val is equal to digit dot lexval. Understanding? This is the value taken from the lexicon analyzer. So this value is copied to f dot val like this. F dot, because we have the rule f dot val is equal to digit dot lex val. Now one operand is here. Now let it be. Another operand, it is here, digit dot lexval is equal to 5. It has to be copied to f dot val like this step, previous step only. So second operand we have here. Okay, then this 3 we need to copy from left hand side to right hand side. See, here also we have 3. So how to get this? By using this. T dash dot inh is equal to f val. So here we will get 3 with the help of this rule. Okay, T dash dot inh. Now it is inherited. Inherited is nothing but f dot val. Left to right. We are copying the operand from left to right. So 3 is here and 5 is here. Multiplication has to be taken place, right? So using this rule, T1 dot inh is equal to T dash dot inh into f val. So this T1 dot inh 15, you can see over here, will be computed with the help of this operand. This 15 value is obtained from operand 3 and operand 5. 3 into 5 into multiplication is here. 3 into 5 is equal to 15. It is obtained. If it is INH only, then how can we pass value from bottom to top like this? Whether it is possible? No, right? So, we have to call this 15 as synthesized value. If we call it as synthesized value, then only we can pass a value from bottom to top. So, using this rule, T dash dot inh is copied to T dash dot syn. Now, T dash dot syn is 15. Once we have value in synthesized attribute, then we can pass it to the higher level, that is this level. T dash dot syn is equal to 15 now using this rule. T dash dot syn, this one T and T1 actually they are same. T1 dot dash syn is equal to T dash dot syn. Means T1, this value is copied to T dash dots in using this rule. Then finally we have reached the last step, T dot val. What is T dot val? It is here. T dot val is equal to T dash dot syn. See, in T dash dot syn what we have? Value we have 15. It is copied to T dot val. So in this example, we have seen how to pass value from left to right, top to bottom, as well as bottom to top. This is an example for inherited attribute. So you may get question like this. Write semantic rules or example for inherited attribute which is suitable for top-down parsing. This is the grammar suitable for top-down parsing, and the previous slide, this is the semantic rule or SDD suitable for bottom-up parsing. Okay, fine. Next, annotated parse tree. It is a special parse tree which shows the values of attributes in each and every node. Okay, now we will consider this as our grammar. L gives En, E gives E plus T or T, okay, like that. Now, just clearly you have to observe this diagram. Now, it is annotated parse tree. There are some problems, okay, so please be concentrated on this topic. Annotated parse tree. What is annotated parse tree? It is nothing but a parse tree showing the values of attributes in each and every node. So this is the annotated parse tree for 3 into 5 plus 4. N is the end of the string. 3, how will you get 3 into 5 plus 4? First L gives En, then we have to use E plus T. For this E, we have to get T. Then T is nothing but T star F. Okay, T gives F gives digit. Okay, like that. The parse tree you know how to write. Okay, so first try to write the parse tree, simple parse tree for getting this expression, and then think about annotated parse tree. Okay, clear. Now let me explain how to write the values and all. So in the expression, first operand is 3. Okay, so digit dot lexval is equal to 3. So from here, since this is the SDD which is suitable for bottom up parsing, easily we can pass value from bottom to top like this. F dot val is equal to 3 and then T dot val is also 3. Then the second operand, that is nothing but 5. 5 is here. Pass value from this step to this step. F dot val is equal to 5 now. Now multiplication takes place. So T dot val is equal to 15. Okay. If T dot val is 15, then E dot val is also 15. So we have 3 into 5. First part is over. 15. For our addition operator, we have operands 15 as well as 4. 4 T dot val is equal to 4. We got like a previous case. Now addition takes place here. 15 plus 4, that is 19. 19 E dot val, which is copied to L dot val. So this is the annotated parse tree for the string 3 into 5 plus 4n. So we need to write annotated parse tree for all those examples. 1 into 2 into 3 into 4 plus 5, 2 into 3, 2 plus 3 into 8 minus 3 followed by n. Then this example. One problem I will solve for you. I will show you. That is problem B. 2 plus 3 into 8 minus 3. First you have to get this star operation, right? So L gives En, E gives T, T gives T star F. Okay, once you got this one, then just consider parenthesized 2 plus 3 and parenthesized 8 minus 3. So I will use parenthesized E like this, parenthesized E here, then E gives E plus T for 2 plus 3, E gives T, T gives F, okay, like this. Then 8 minus 3, E minus T I will use, okay, then E gives T, T gives F, F gives digit. Similarly, T, F and digit, all operands we have now. So how to copy the value from bottom to top? So first operand is 2. 2 is here. So write digit dot lexval is equal to 2. And one more thing here, you can see the entire problem solution now itself. But actually how to solve this, don't write this value in the beginning. Make it blank. Just write L dot val is equal to and blank. E dot val is equal to. T dot val is equal to. You have to fill later. It is bottom up approach. So here we have digit dot lexval is equal to. Now fill this 2. Okay. If we have this value, then f dot val is also 2. Now fill this value. F dot val is equal to 2. Then t dot val is equal to 2. E dot val is also 2. Like that you have to fill. Plus another operand 3. Next write this digit dot lexval is equal to 3. So f dot val is 3. T dot val is also 3. Similarly here digit dot lexval is 8. So f dot val is 8. T dot val is 8 and E dot val is 8. Then last operand 3. Digit dot lexval is 3. F val is 3. Then T val is also 3. 8 minus 3, that is 5, like here, like this. Similarly 2 plus 3 is 5. So you will get f dot val is 5 as well as f dot val here 5. 5 into 5 you will get 25. 25 is passed from T dot val to E dot val, E dot val to L dot val. Final value is 25. This is how to write annotated parse tree. Student, please write the annotated parse tree for A and C. That is a homework for you. Evaluation order for SDDs. See, in the previous annotated parse tree, we don't have any order how to evaluate the expression. Since we know that it is bottom up parsing, we have started from bottom to top like this, but it doesn't say anything about the evaluation order. So for that purpose we have dependency graph, data dependency. It is a useful tool for determining the evaluation order for the attribute instances in the given parse tree. Each attribute is associated to a node. That means this point is very important. If we have inherited and synthesized attribute like this, they are considered as two separate nodes. Okay, see here t dash dot inh and t dash dot sin. This inh is one node, this sin is also another node. Direct edge indicates dependency graph edge. Direct edge means solid edge, and dotted edge indicates parse tree edges. So first you need to write parse tree and then dependency graph. Consider the example which is suitable for top-down parsing. I'll explain how to write dependency graph for this example. This is our annotated parse tree for 3 into 5. T gives ft dash, then star ft dash, that is you will get the multiplied answer for 3 into 5. So how exactly values have been passed? So, just to observe the starting point here, digit dot lexval, that is number 1. Number 1 is given. Then another operand is here, digit dot lexval, number 2 is given over here. And one more thing, please note down, the numbers are not at all important here. You can give the number 1, 2 like this, then 3, 4 like this. Okay, only the writing of edge is very important. See, we are copying value from here to here, digit dot lexval to fval. So arrow mark is like this, and here from digit dot lexval to fval, arrow mark is like this. Now we are copying value from left to right like this, because multiplication takes place here. One operand is here, it has to be copied from left side of the tree to right side of the tree. So the arrow mark is like this. T dash dot inh is nothing but f dot val. So we have one operand here, we have another operand is here. Multiplication takes place here, no, in this particular step of the past. No. So there is an arrow mark from here to here. T dash dot inh to t dash dot inh, this arrow mark, and one more arrow mark from here to here, because t dash dot inh will get its value. What is t dash dot inh? That is here, see, 15, no? So how will you get this 15? By multiplying this 5 and 4. So there is an arrow mark like this. So 15. See, now we have 15 over here. That 15 has to be called as synthesized. See, here t dash dot inh is 15 and t dash sin is 15. So to call it as synthesized attribute, we have an arrow mark like this. Okay, so now final value 15 is with us. With the help of synthesized attribute, we are passing the value to here, from here to here. So this is dependency graph for 3 into 5. Will you able to write the dependency graph for previous annotated parse tree? I mean this parse tree. Easily you can write now. So let me show. Okay, these are the different problems of dependency graph. You have to write the dependency graph for all those problems using this SDD, text calculator SDD, not by using this one. Okay, this is suitable for top down. We will write the dependency graph with the help of this one. This example I will show you. First write the parse tree using dotted edge like this. 2 plus 3 into 8 minus the same example I took for the simplicity purpose. So there are two types of edges. One is dotted edge, another one is direct solid edge. Dotted edge means it is parse tree edges, and solid edge means it is dependency graph edges. Start from here, and here also the numbering I took the first number I have given over here, number 1 first operand, number 2 second operand, then this value is copied over here, so 3 I have given here, then 4 here, next 5 and 6, 7 and then 8. Please students, please note down, no need to give the number like this only. One more thing I will tell you, in another way, you can give number 1, 2, 3, 4 like this. Then 5, 6, 7, 8, 9, 10, 11, 12 like this. Okay, in any way you can give, but one thing you observe, see this node is there, no, e dot val is equal to 5. This node is having value 8. It should be greater than these two nodes. Why? This node will get its value only after evaluating these two nodes. That one point you need to remember before giving the number to the nodes. Okay, understood? No? This node will get a value only after evaluation of this. So, these values are always smaller than this. Similarly, you can't give numbering like this 1, 2, 3, 4. Sorry. Okay, 1, 2, 3, 4, 5, 6, something like that you can't give, because this node will get its value only after evaluating this one and this one. So the numbering should be like this 1, 2, 3, 4 or something. After evaluating this node can be given a number. See, this is 16, this is 18. Okay, it is left to you, but arrow mark is important. Pass value from here to here like this, then like this, e dot val will get its value. Okay, one more arrow we need here. Okay, just I forgot to put here like this. Okay, then f dot val will get its value 5, t dot val is also 5. Now multiplication, so an arrow mark from here to here, here to here, as well as here to here. 25, it is copied to e dot val, and finally l dot val is 25. This is called as dependency graph. Please solve these 4 problems. This is the last part of this chapter, application of syntax directed definition. It is mainly used to construct syntax tree. What is syntax tree? It is something like our parse tree, but syntax tree interior node is always operator like plus. Let me draw, if possible I will try. E1 plus E2. How will you write parse tree? E gives, sorry, E1 plus T. This is our parse tree, right? So syntax tree contains interior node as the operator. That is, we can write the syntax tree like this. Plus gives E1 and E2. Means for this plus, operands are E1 and E2. That is the main difference. Understood, no? Okay. Now formal definition we will see. Syntax tree node representing expression E1 plus 2 has a label plus, as I wrote earlier, label plus, and 2 children representing E1 and E2. Each node is implemented by the objects with the suitable number of field. Each object will have op field, that is the label of the node, with the additional field as follows. Means here op field means it is operand or operator. Okay, op can be operand or operator. Then if the node is a leaf means terminal, then additional field holds the lexical value. If I have a terminal digit, then its value. Okay, value for the leaf. It is created by the function leaf of op comma value. Op is the label. If it is digit followed by 5. Understood, no? I am going to create a leaf for number 5. How should I write? Op is nothing but label. I will use digit, comma, val is 5. So leaf of digit, comma 5. It is how to create a terminal or the leaf node. Suppose node is interior node, means for like this. Okay, operator plus is there. Then we have to create a node followed by op means plus, then C1, C2 up to Ck, any number of nodes depending upon the expression which you are going to use. Okay, here in this particular slide you need to remember two functions. One is leaf function, another one is node function. Leaf function is for terminal and node function is for creating operator. Consider this, it is also important. Explain that one of the applications of syntax directory definition, or directly they may ask you to construct a syntax tree with the help of SDD. This is an example. Construction of syntax tree using simple expression. Simple expression means desktop calculator. SDD we will use. Steps in construction. First go through the steps. Okay, which is the expression taken? A minus 4 plus C. Right? A minus 4 plus C is the example taken. So operands are A, 4 and C. Okay, are you getting? Operands are A, 4 and C. How to create an object? P1. Object P1 is a new is the built-in function used to create a new leaf or new node. If it is operand, then create leaf node, leaf of id. Id means, what is id? I mean, remember this one, op comma val. So op means label, so label I will use it as id, identifier, and entry for a. Entry means symbol table entry for operand a. We don't know exactly the value of a, so it's symbol table entry for a. Next, another operand 4 we require. So P2 is equal to new leaf node. The label I will use is it as num, then number is 4. After that, a minus 4 has to be computed. So new node minus P1 comma P2. P1 and P2 are the objects which we have created now. So create a node with the help of label minus followed by two objects P1 and P2. Okay, a minus 4 is over, then plus C. How to compute plus C? C has to be created, so new leaf node with id comma entry C. Then last one, finally P5 is created with the help of node, label is plus, the operands are P3 and P4, previous two objects. These are the steps for creating syntax tree. Now, this is our syntax tree. How to write this? So first step, you have to create parse tree for a minus 4 plus c. Now one thing you can observe here, there are three types of edges. First edge is parse tree edge, dotted edge. Second edge is dashed edge, like this. Okay, like this dashed edge, you can see that edge represent the data dependency between syntax tree and parse tree. Okay, data dependency between syntax tree and parse tree is given with the help of dashed edge, like this. One more edge which is remaining, solid edge. Solid edge, this one, right? So this is solid edge which represents syntax tree edges. Okay, understood? Three types of edges. One is dotted edge, parse tree edge. Another one is dashed edge, that is relationship between parse tree and syntax tree nodes. And the last one, solid edge, that is nothing but syntax tree edge. Expression is a minus 4 plus c. So I will consider e gives e plus t. This e gives e minus t. So e gives t, t gives id. Okay, like this. So you know how to create parse tree for the expression. Okay, no need to explain again, I think. Now consider how to construct this. Okay, first consider leaf nodes id. Id is constructed like this with two fields. First field is label, second field is pointer to symbol table entry. So write two entry for A. Another edge you construct like this, another node, number with two fields, leaf node with two fields, number followed by particular number. Then A minus 4. A minus 4 means there are two children for this node minus. So we have total three fields here. One is minus, another one is this field first operand, this is second operand. Okay, A minus 4 is computed. Then plus. For the plus, once again two operands. First operand is this minus and second operand is id. So easily you can write the syntax tree. Now what about the dashed edges? How to write this dashed edge? This id is here. This id is corresponding to this node, t dot node as well as t dot node as well as e dot node. So there are two dashed edges like this. Okay, then for this minus, I mean relationship between this particular node of syntax tree and this node of parse tree. Minus corresponds to this node only. Then what about this 4? This 4 corresponds to this t dot node only. Then this plus corresponds to e dot node. This id corresponds to t dot node. So that is the relationship between parse tree node and syntax tree nodes. You can take any different examples for construction of the syntax tree like a plus b minus 4. Okay, something like that. Or any one example is one example I have shown you. So this is about syntax tree definition and syntax tree translation, annotated parse tree, dependency graph and construction of parse tree. So this is about first chapter of module 5. So in the next video let us consider about intermediate code generation. Thank you all. Happy learning.